All right, everybody, let's get started. Good afternoon, folks. Welcome to the North Carolina Museum of Natural Sciences. Welcome into the SCCU Daily Planet Theater. It's great to see folks turning out for today's Lunchtime Discovery Series. If you're tuning in online as well, thanks for joining us. Glad you're there. Sound off in the chat. Drop little waving hands emojis to let us know that you're there, or let us know where you're viewing from. We always like to meet everybody who's participating in our programs here at the museum. My name is Chris Smith. I'm the coordinator for current science programs, and I'm your host for the Lunchtime Discovery Series. I get the pleasure and the privilege of introducing you to our guest speakers, but first, I have to thank the folks who actually coordinate and organize this program that we do here at the museum every single week, and that's the Office of Environmental Education. Over next door to us in the Department of Environmental Quality, so over in DEQ, they're doing fantastic work. And then with us here at the museum, we can bring this great program to you almost every single Wednesday at noon, where we get the opportunity to meet interesting people who do interesting things out there in the worlds of science, nature, and beyond. And today, I think we're doing a little bit of the beyond as we think about what's going on outside of the planet, outside of Earth, with today's special guest. Did anybody, hopefully I'm not preempting our guest speaker's talk, but how many of you grabbed your cell phones back in November and rushed outside to try to snap a picture of the Auroras in North Carolina? Did anybody? Was it not even Patrick did? Okay. It was just me then. Okay, that's fine. I'll be the nature nerd in the room. Well, I'm not used to seeing auroras in North Carolina. In fact, I had never seen one until I think last year, when finally the Auroras decided to stretch far enough south for me to be able to catch a glimpse of one using technology, special cameras like iPhones, in order to do it. And so I'm excited today to maybe get a little bit more of the science behind that, what made it possible. When's the next one, Tony? That's what I really want to know with today's guest speaker. So I'll go ahead and bring him up. Everybody, Tony Rice is a NASA JPL Solar System Ambassador and a science contributor for WRAL TV News. You can find his writings online with WRAL and more. And you can often find Tony here at the Museum of Natural Sciences, sharing his space science and knowledge with us. So please put your hands together and welcome him to the stage.
Thank you very much. So we're going to have some fun today. We're going to talk about the aurora that we have been able to see recently, as of last year, as far south as North Carolina. We're actually able to see it even farther south than that. There were reports down into New Mexico, Texas, even down into Florida. I've got a friend I work with who is in Miami, and they were actually able to see it down there. A little more of a challenge in some of those urban areas because of light pollution. That's always the story with anything in the sky, is the two things that are fighting against us are often the clouds and light pollution. So hopefully at the end of this, you'll have a little better understanding of why 2024 was so special, why we're actually still excited about 2025. So to answer your question, when are we going to be able to see it next in here in North Carolina, or even farther points south? The answer is, I don't know. You'll understand a little better why, because we're talking about space weather here. We're talking about something that requires prediction, it requires measuring the atmosphere out there, and in this case, we're talking about the sun's atmosphere, believe it or not, and also our atmosphere, because it's that interaction that is actually what you're seeing with the aurora. But we don't know because there's a lot of chaos going on out there. But I don't know, but there is a good possibility that we might be able to see it in 2025. And I'll explain why. So let's jump into it. So the images you got up on the screen right now, I actually took that out at Jordan Lake with my lowly iPhone. If you had the opportunity to go out and try and take some images, maybe you had some success, maybe you didn't, I've got a slide with some tips on how to do that. It's specific to iPhones, a couple of the little buttons that you have to press there, but it is possible with most late model cell phones. And if you've got a higher end SLR camera or something like that, the same principles apply there. It's all about leaving that shutter open for the maximum amount of time and staying still, but we'll get into that. So what is an aurora? Why does an aurora happen? This is why, the sun. So this is an image of the sun. These are actually many images thrown into an animation. It was taken from a spacecraft called the Solar Dynamics Observatory. I believe there's actually a exhibit. Patrick, keep me honest here. You pass it every day on your way into work. Patrick is one of the astrophysicists here at the museum. Is the SDO exhibit still up there? Awesome. So go up and see more about SDO. SDO is a really amazing spacecraft. It has a number of telescopes on board that are looking at different wavelengths of light. And there are some wavelengths of light outside of what you and I are seeing each other with today in the visible spectrum. When you look at very specific wavelengths of light, you can see some very specific structures on the sun's surface. Over there on the left-hand side, that's one of those telescopes that's looking at a very specific wavelength of light, and you can see the activity that's going on there. The sun is very, very active. So the too long didn't read explanation as to why we are able to see aurora so frequently right now is that the sun is very, very active. We're at a point in the sun's about 11-year life cycle called solar maximum. We declared, or I should say NOAA declared solar maximum back in October, around the time that I took that picture on that first slide there, when we were able to see the really, really brilliant aurora as far down as South Carolina and on down into Florida. But if you kind of watch here, you'll see over on that upper left-hand side some loops that are occurring. That is plasma. That is all sorts of material that the sun is belching out following magnetic field lines. Over on the right-hand side, that is a little different instrument. It's measuring magnetic fields on the surface of the sun. This is what you're seeing here is the photosphere, that part of the sun that you're not supposed to look at any time. Don't ever look at that. If you had the opportunity to see an eclipse recently, you wore the eclipse glasses so that you could block enough of the light to be able to see that photosphere. Some of these sunspots are big enough that with the naked eye, if you've still got your eclipse glasses from back in 2017, or if you're lucky enough to travel and see the eclipse in 2024, last year, you can still use those eclipse glasses and see some of these sunspots. These sunspots are a measurement that we use to understand activity on the sun. Because if you kind of visually match up these two images here, you see that group of like 4 sunspots that's rotating around. You match them up over here and you can see some of that activity that's going on. Those sunspots are cool spots on the surface of the sun. And the process that the sun is going through internally, it's pushing all of this energy out, and it's got to make it around those cool spots. That's what creates this chaos. That's what creates these loops that you see occurring there. Those loops are strained with all that extra energy to the point that sometimes they will snap like rubber bands. When that occurs, we have what's called a coronal mass ejection. That spits out, kind of belches, gas, charged particles, plasma, and that pushes all of that energy and all those particles out into space. Keep in mind that while this looks like a very two-dimensional thing, and all of the images that I'll show you today, very two-dimensional for obvious reasons, the sun is three-dimensional. It's a sphere. It rotates. What you're seeing here is the natural rotation of the sun. Those sunspots rotate around, and sometimes they get to kind of the center point there. And if it's along that center line when that coronal mass ejection occurs, those are the ones that we worry about. Those are the ones that we pay attention to. These that are occurring over here, those happen all the time. They're spitting out towards Venus or Mercury or wherever, and we don't worry about them so much here. But when those happen to rotate around and they're all along that center line, that can create what's called an Earth-directed coronal mass ejection. So I have an image from a different spacecraft. This is called SOHO, the Solar Heliophysics Observatory, and its purpose is to monitor the sun's corona. We're watching that atmosphere around the sun. Now that blocked part in the middle, it's an artificial eclipse is what it's called. Literally a little disc on the camera, and there's 2 different cameras here. We've overlapped 2 of them, the C2 and the C3. The blue image is a little bit wider. You can see more of the corona, a little more detailed on the red image. But researchers use this to better understand what the sun is doing. And you can see coronal mass ejections that are occurring. Now watch this loop as it happens over and over again, and I'll explain That's going across in a second, and that dot over there in a second. But I want you to focus on the center of that image. Notice that a halo occurs. So when a coronal mass ejection occurs, Earth-directed, meaning it's pointed directly at us, we will see a halo effect. We'll see that material kind of expand out. The best way to think about it is if somebody blew a smoke ring at you. You could walk right outside right now and just simply use your breath to blow a smoke ring. But if they blow it off to the side, it doesn't look like a circle. But if they blow it directly at you, you're going to see that circle widen, widen, widen. So when we see that on a SOHO image from the LASCO instrument, and we see that circle widen, 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 we know that that's Earth-directed. That's something that we need to pay attention to. That's kind of the first step in when is the next aurora going to happen. When we see an Earth-directed CME, we know that there's material coming our way that could create aurora. And I'll show you in a second how that works in a little more detail. But let's talk about the elephant up on the screen. You see that line coming up over there? Anybody in the audience have a guess of what that might be? It's a comet. So if you remember back last year, there was a couple of comets that we were pretty excited about. This is Comet Chechushan. I believe it was I want to say 23 Chechushan Atlas. And comet naming is fun. It always starts with a C. The next 4 digits are the number that it was discovered. And you notice those numbers tend to be very recent because comets don't tend to live very long. They break up, especially when they get close to the sun. And the other name is generally for wherever, whatever observatory it was discovered at. And then you'll see Atlas mentioned, and there's NEOWISE, and that's the sky survey or the spacecraft or whatever was used to discover it. But that's Chechushan, which we actually got some pictures of. It was visible from North Carolina. And the other dot that's moving along there, I believe, is Mercury. So we see Mercury quite a bit in LASCO images because it is so close to the sun. So CME occurs, it's Earth-facing, it's Earth-directed. Here's what's happening. The solar wind is carrying those particles towards us. And Earth has a protective magnetic field around it. And it's donut-shaped. So you can think of this magnetic Krispy Kreme donut that is sitting around us. Now picture that donut. Yes, the side is protecting us, but the top is not there. You know, we're not talking a dough ball, we're talking a donut. There's a hole in it. So what will happen is those magnetic field lines that exist in that magnetic protection as well, the solar wind will follow those to the top and the bottom, to the poles of the Earth. So that's why we tend to see aurora, either Aurora Borealis near the North Pole or Aurora Australis in the South Pole. We tend to see them closer to the poles. In order to be able to see an aurora farther south, you need a lot of energy. You need a very significant CME with a lot of power behind it, a lot of those particles. There's a couple other things in there that have to be just right. The polarity of that CME actually matters. And that's something we can kind of guess based on the time of year, just by seeing it in that LASCO image, but we really don't know until it gets close. I'll review a couple of the spacecraft that we're using here to do some of these predictions. But this is what's happening here. It's following those magnetic field lines to what we call the auroral circle up at the North Pole and down at the South Pole. And when that happens, that can create some aurora. So here's another image that really shows an Earth-directed. This is sped up, of course. You can see the time frames going down there, but it gives you an idea. And there's Mercury photobombing again. There's a very active section of the sun over on that left-hand side, but some sunspot rotated around to that center line, and that CME occurred right at a point where it was facing Earth. So the CME has occurred. It's Earth-directed. We've got material going towards us. What happens from there is all of those charged particles are interacting with the upper atmosphere. That's what you're actually seeing in an aurora. Those lights that are occurring are interactions with oxygen, nitrogen, and we can tell roughly what element is being interacted with in the atmosphere, and also how high it up is simply from the colors. And this gives you an idea of what that looks like. So the past couple that we've seen here in North Carolina were mostly in the red range. It kind of gave the sky a bit of a magenta look to it. We saw a little bit of purple in there. We did also see some slightly different red tinges to it that weren't horizontal, they were more vertical. Those are called SARs, and those are really fascinating, A, because you don't see them very often. That is, the best way to think about this is what you see on the screen right now. The aurora that are up horizontally are reflecting interactions from that material coming from the sun, interacting with the Earth's atmosphere. SARs, where you see the kind of stripes going up or vertically, that's interaction with our atmosphere, heat energy that's coming from Earth and moving up into space. We actually saw, not only was it rare to see aurora at all in North Carolina, we saw as far down as New Mexico, some of that rare SAR activity. Earth isn't the only place that you can see aurora. We photographed aurora on Jupiter. We photographed aurora on Saturn. We see it quite frequently on Saturn, as a matter of fact. Any planet that has an atmosphere and has a magnetosphere, that Krispy Kreme donut that I was talking about, it is possible to have auroral activity. So why 2024? And why do I have some confidence that we might see this again in 2025? The answer is the solar cycle. So this first slide I'm throwing up here, this is from the Space Weather Prediction Center. I'm going to dive deep into that in a little bit. We've got some folks that work for NOAA. There's a NOAA National Weather Service facility on the NC State Centennial campus over here. They're focused on terrestrial weather. They're focused on whether we're going to get snow this weekend or not. There is another group out in Colorado that is focused on space weather. Space weather is important, not just so we can figure out when we might be able to see aurora again, but it is important to safeguarding assets out in space, protecting satellites, protecting astronauts. They focus on this solar cycle progression very, very intently. They're the ones that went ahead and declared that we had reached the maximum. So this cycle is about 11 years long. And I say about because it kind of does what it wants. And we can predict what's going to happen along that curve. But as you'll see in the next slide, this past solar cycle outperformed. And that's the reason we saw so much activity in 2024. But like a roller coaster, yeah, it's fun going over the top of that hill, but your fun doesn't end at the very peak. You're still going to have a lot of fun on the way down too, and that's where we are right now. The top of the solar cycle, it can continue for another year. So yes, we first saw some decent activity in North Carolina back in May. That can continue over the next couple of months, possibly throughout the year. We don't know yet. Right now, the sun is doing the same thing it's been doing for the past several months, past year, actually. It all kind of comes down to, is that Earth-directed CME going to hit us again? So this is the last couple of solar cycles, and they're numbered at the bottom, 21, 22, so on and so forth. We're at the peak of 25 right now, and you can see that we way outperformed what they thought might happen. They ebb and flow like anything else. It still didn't top out at what we saw back in the 1980s. We do expect it is going to start slowing down here. This is a little bit deeper dive into 25, and you can see what that red line was, the prediction that was put in place at the end of cycle 24, really outperformed. The gray scale there is kind of natural error that they were expecting in there. We expect, here's our target in the red line, but we expect it might go above or below this. Turns out it really went above it. So it's going to continue to be pretty active. We could possibly see something in the next couple of weeks. We'll see. So let's talk a little bit about space weather itself. It's coming from the sun and the atmosphere immediately around the sun, the corona, is actually one of the things we know the least about in our solar system. We've got a number of assets out there. I mentioned the SDO, the Solar Dynamics Observatory. I mentioned SOHO is keeping an eye on the sun. We've also got Stereo A and Stereo B, a pair of spacecraft that were put in place to be able to see the 100% of the sun. We can put it on the far side, we can put the other one on the near side, and be able to study it in total for the first time. So we got a number of them out there. The reason there's been so much effort put into it, A, we don't know enough about the sun, we need to understand more about it, but it has impacts here on Earth. When there are extreme CMEs that hit us, when there's extreme solar storms, it can even impact GPS. And there have been times where it has impacted farming. Farming today is so reliant on GPS technology that when those GPS signals, it's not that they go out, it's that they're sometimes inaccurate, which is even worse. So we must maintain those kinds of systems. It can damage electronics on the satellites themselves. It can damage solar panels. So this is a graph tracking SOHO, the spacecraft that was producing those blue images we saw before with the comet in it, and being able to see those CMEs. That's the performance we've seen over the years as it gets hit with the solar wind over and over and over again, and those stronger coronal mass ejections, it degrades the performance of those solar panels. And this is just an example. This happens to every spacecraft out there. Most of the satellites that are orbiting Earth are solar powered. We do use nuclear power on some other exploratory missions. Those tend to be more deep space missions. So this is impactful to absolutely everything that's out there. Communication satellites, weather satellites, you name it, they're using solar power. This can actually impact star trackers. So one of the ways that a satellite maintains its position and its orientation, to make sure it's pointed in the right thing, because ultimately 99% of those satellites out there are pointed back at Earth. They're either observing Earth or they're transmitting data or images or whatever. So they've got to be pointed correctly. They use what are called star trackers. There's a catalog that's on board, a little database that says this is what the sky looks like. Compare it to this generally just fairly simple telescopes with fairly simple imaging with digital cameras. Compare that to your database and make sure we're pointing in the right direction. Well, these solar weather events can blind those cameras temporarily, and it can be enough for them to, in some cases, lose control. Had that happen a time or two. So that's one impact. The other impact is atmospheric drag, and this is actually very interesting to me. This is happening all the time. When we think about our atmosphere, we're down here at ground level, we're breathing the atmosphere. As you go higher, 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 it gets thinner. It's not like there's a line where space begins. It gets gradually and gradually thinner, but it doesn't do so evenly. The upper atmosphere can get lumpy. It can be a little denser in some places and a little thinner in others. When you've got a satellite, any spacecraft that's flying through that difference in density affects its orbit and it can actually throw it into a different orbit. And the solar weather can impact that. As a CME hits the upper atmosphere, it will cause that air to get denser. And that can really throw things off. So the graph you see over on the right-hand side, that is, I pulled it last night off of the International Space Station. That is showing the altitude of the International Space Station. They periodically, every couple of months, have to reboost. Now, the station doesn't have engines on it like a rocket would. It does have attached spacecraft that do have engines on board. So periodically, they'll schedule this out where the station will be boosted up. And it's simply to prevent it from deorbiting. So if the question ever comes up, how do we deorbit the space station? We want to do it in a planned way so it comes down where we want it to come down. It eventually will have to be deorbited at its end of life. But if we were to do nothing, it would deorbit on its own because of the sun's interaction with the upper atmosphere. You will see video of one of the astronauts getting into the middle of the ISS on one of the long hallways that is perpendicular to the Earth's surface about the time they were going to do a reboost. And the station moves around him as it's reboosted up, which I just think is so much fun to see. The other thing we have to think about, because we do have people up there on the International Space Station, we do have astronauts that are planning to go beyond the International Space Station as we look to explore the moon and on from there. this space weather can be pretty dangerous to them. And I purposely put up our Artemis II crew. Anybody recognize a face there? Christina Cook, yeah, she's been to the museum several times. She's our North Carolinian. She went to the School of Math and Science here in North Carolina, and she's also a proud NC State graduate. So Christina is very much looking forward to her turn on Artemis II, that it's going to go out past the moon, and she will be one of the people who has been the farthest from Earth. And I'll give you one example of a space weather impact of a particular satellite. Back in '98, this event cost an estimated $250 million, and it took out a bunch of pagers. Remember those? Yeah, those were a thing back then. It could happen again with our current infrastructure, but it took out CBS Radio, all their TV feeds. But actually the impact that was felt the most, and you'll read about the most, was the CNN airport network. Got completely taken offline because this particular satellite failed because of a space weather incident. I mentioned a couple of spacecraft, STO, SOHO, but there's a lot of others that are out there studying heliophysics. I just kind of wanted to throw them up there so you can get a bit of feel of what's going on. GOES is one that you see every day on the evening news. It is the main weather satellite for North America, but it has a number of instruments on board that monitor space weather. The other one that's really important, and I'll show you a little bit more about this one in a second, is Discover. That is a joint NOAA and NASA spacecraft mission that is measuring space weather. So I talked about solar minimum, solar maximum. This kind of gives you an idea of what this looks like. It's a different view from SDO. See how very quiet the left looks? There's no sunspots. We measure the increase towards solar maximum based on those sunspots. And that one was back in October 2024 on the right-hand side. So I've talked about NOAA's Space Weather Prediction Center. You've probably seen the scales for tornadoes. You've seen the scales for other terrestrial weather. We have a scale for space weather as well. I'd like to kind of transition a little bit into how you use this information to better understand when we're anticipating that we might be able to see some aurora, what some of these things you're seeing online and in the news mean. The column to really pay attention to, the two, are the left-hand side. That's the degree of the storm. And it's the same kind of nomenclature we use here on Earth between a minor and an extreme. They are same kind of rarity. Minor storms are common. Extreme ones are extremely rare. In the 11-year cycle, we only see about 4 days worth of extreme storms. And we saw all 4 of those last year. We could see more this year. The other thing that you pay attention to is the KP factor. And that stands for a German word that basically means the planetary index. It is the magnetic potential, the energy potential of the Earth itself. We've got to have a KP up to 9, and it tops out at 9. So you'll never see a number bigger than that. If you see a number bigger than that, delete that app from your phone. They don't know what they're talking about. They're making up data. 9 is the top. It's got to be at least 9 before it's strong enough to be able to be seen here in North Carolina. The map up in the upper right, it's kind of hard to see that red line. The red line extends down to just into southern Virginia. And what that's representing is where you would possibly be able to see aurora overhead. That's the other component of this. Just because you're not able to see aurora overhead, it hasn't pushed down far enough to be, directly over Raleigh. Because this is happening so high in the atmosphere, things that are happening way up there, we might be able to see here in North Carolina, even if they're happening, say, in upstate New York. And that's what happened back in October. The overhead activity was up in the Newark metro area, but we could see it down on the horizon. And that will happen a little more frequently as well. This is the NOAA Space Weather Prediction Center's Aurora dashboard. It is probably your best resource. It's free. You can go on it. Your phones right now, it's available on your desktops or whatever. And it has predictions for the next 24 hours, and it has predictions for the next several hours. And that's because we don't really have a good idea on what that solar storm actually is, how it's charged, how strong it is, its polarity, until it gets closer to Earth. I will say that its examples here and the maps that it throws up are extremely, extremely conservative. So if you go on there and you see that this green blob is all the way up in Canada, it doesn't necessarily mean that we won't see anything. Again, you might see it low on the horizon. You might see it, you might actually see it overhead, because again, they're very, very conservative. The other part of the Space Weather Prediction Center's website is a bunch of charts and graphs and numbers. We love these things. They're color-coded. You need to get to that nice deep red before we're going to be able to see anything here. This was taken last night, so you can see we're in a mild storm condition right now. The chart over on the right-hand side has some predicted numbers. There you're looking for the number closer to 5 in order for us to see some activity here. They have a really hard job at the Space Weather Prediction Center. It's hard enough predicting weather here on Earth, but to do it out in space is even worse because they have so little data available to them. We saw SDO, we saw the LASCO instrument on the SOHO spacecraft. That was the blue ones where we got the nice smoke ring pointed at us. That's great. That gives us a little bit of information about what it might be like, but that is remote data. Those are images. We don't actually get to use or gather what's called in situ data, meaning it's measured right there, and we can touch the environment that we're measuring until it gets to what's called the L1 point. And that's because that's where we have a couple of spacecraft. These are Lagrange points. They are points of balance in our solar system, balance between the Earth, Sun, and Moon. And they're great places to park spacecraft because we can put them there and we can leave them there and we don't have to burn a bunch of fuel. That's what kills spacecraft, is fuel. You need fuel to keep it in that right position, to keep it pointed the right way, to keep it in the right position in space, to be able to do its job. We put these spacecraft in a halo orbit around that Lagrange point. L1 is between the Sun and the Moon and the Earth. It's beyond the Moon, and this is a great place for solar missions. L4 and L5 are where we have the stereo spacecraft, and then L2 is where we have the James Webb Space Telescope. It is a perfect place to put it because it's shielded from solar energy by the Earth, and it's far enough away that we don't get all the noise from Earth radio and other noise. It uses some cameras that require an extreme cold, so it's a perfect place to put the Webb telescope. And anybody a baseball fan here? All my talks tend to end up with some sort of a baseball slide on it because there's so many comparisons I can make. I said that the NOAA folks have a hard time doing this. The reason it's so hard is because that L1 point, when you think of it in terms of a baseball diamond, the pitcher throwing the ball to the catcher and the batter. The L1 point, if you were to think of it in terms of the distance between home plate and the pitcher, it's about the top of the batter's box. So you may have heard that Major League Baseball batters have something like 400 milliseconds of decision time. That's how much time they have to actually see the ball before they have to hit it. That's the same kind of situation that we're dealing with space weather, because the only place we can put these instruments is at L1, which is a mere 1 million miles away, but the sun is 93 million miles away. Let's put that in a little different perspective. So I'm standing in the Daily Planet. This sphere that we're all sitting inside right now is, I believe, 42 feet tall, basically 3 or 4 stories tall. So it's about a 1 to 100,000 ratio to the real Earth. If we were to apply that to the map, where would L1 be for this version of Earth, for the Daily Planet version of Earth? It turns out it's the YMCA on Hillsborough Street. It's about a mile away, a little bit less than a mile away. So it's 0.93 miles is where that L1 point would be. And I very much want to put a James Webb Space Telescope model at the cookout over on New Bern, because that's where L2 is. But Okay, the sun is actually out in Lexington. It's on past Greensboro, it's past Winston-Salem and all that. It's almost to Charlotte. That's a long way away. So I do a lot of work with TV meteorologists, and when they get a little salty, and some of them do, about why don't we know more to be able to share with our viewers about when and where aurora might be. The comparison I give them that really fits for what they're doing. So, I need to stop by WRL on my way home. I need to reinforce this to them. They're gearing up for winter weather right now. We're all wondering if we're going to get some snow over the next couple of days. So picture if you were a meteorologist and you had a satellite image of a storm off the coast of California. And then the next time you, as a meteorologist in Raleigh, North Carolina, had any data to make any predictions about what that snow might be like, the storm was sitting over NC State. That's pretty hard, but that's the world we live in with space weather, and we're getting better at it. So, next time it happens, don't know when it's going to happen. I'll have some confidence that it might happen here in the next couple of months, hopefully. Here's some tips on how to do it. The two most important things are keep the phone steady. If you've got a tripod, they're not expensive. You can even get little contraptions that will hold onto your phone and go onto an existing tripod that you may have. Holding that phone steady is really, really important. You're going to get a better quality picture that way, but you're also able to do the other most important thing, and that's leave the shutter open as long as possible. And it really doesn't take long. About 5 seconds is all it takes to get a good quality photo. And you'd be amazed at how much more color and how much more definition you see just from a long exposure, just 5 seconds of long exposure through your iPhone. So iPhones in particular have a night mode. You definitely want to turn your flash off. I made that mistake and blinded some poor person that was standing next to me out at Jordan Lake last time we were out there getting some pictures of the aurora. And you want to have night mode on. So to do that, you swipe up from the bottom, and this differs with some of the older models, but basically all the newer models have night mode. You want to swipe up, and then there's another little slider there, and you can see it down there at the bottom of the image on the right. Slide that all the way over, and that's going to maximize your exposure. If you've got a tripod, use it. If you don't, and I did this because I forgot my tripod, actually, the last time I went out to take some pictures at Jordan Lake of the aurora, find a tree, find a railing. I was standing on a boat dock, so I kind of put my phone up and held it to steady on top of a railing that was holding a life preserver. And 5 seconds isn't a long time to have to stay still, so that will actually work. And the other tip is with the newer iPhones that have multiple lenses, don't bother zooming in. It's just going to make it harder to take the picture. Just use the 1x lens, and you get a better picture that way. So I promised some pictures. There on the left-hand side, these are both from Jordan Lake back in October, right around solar maximum. And you can see we've got that kind of magenta look. So we know that that's oxygen up in the upper most parts of the atmosphere. And I mentioned the SAR, which stands for a stable auroral red aurora, and that is evidence of heat escaping from the Earth and then interacting with this energy that is being added to the upper atmosphere. I took this one from the Farrington Point boat ramp. Another tip, there are 2 boat ramps. It's a great place to go to take pictures like this because it's very, very dark out there. And especially if it's something that's happening in the evening where you're looking out to the west, where there's less light pollution. As soon as you turn around and look towards the east or towards the northeast, you see what we call a light dome. You'll see a glow on the horizon from Raleigh, and you especially see it from Chapel Hill there. So Jordan's a great place to look if you're looking at something in the sky, either in the morning and the evening in the west. And there's 2 places that you can go that are open 24 hours a day. You're perfectly able to go there. Be aware of your surroundings. You're in the middle of the night, but Farrington Boat Ramp is one of them, and there's another one down south of there. So here's another picture that I took recently. This is of that Chicxulub comet that I also took out at Jordan. And the tips are the same there to get these kind of photos. And that's keep it still. I remembered my tripod that time, and long exposure. So this is happening, that was probably about 45, 50 minutes after sunset. So we're still in the twilight hours. We're not quite to what is known as astronomical twilight, when it starts to get really, really dark, but you can get some beautiful pictures that way. So I want to point out two things before we open it up for questions that are kind of tangentially related, astronomy events that are coming up. The first one, what is today? Today's the 8th. So in 3 days, I'm going to be looking at the LASCO instrument on the SOHO spacecraft, because I'm hoping to see what I showed you a couple of slides ago with the Chicxulub comet. There is a comet C2024 G3 Atlas that we're keeping an eye on right now. It's starting to get some hype. And the hype you may have heard about it is that it could be brighter than Venus. Maybe. Not my quote, but it fits perfectly here. Comets are like cats. They both have tails, and they both do exactly what they want. So we don't know what's going to happen with this one. It just recently passed perihelion, which is the closest point in its orbit to the sun. That is when it is at its brightest. The other thing that affects how bright a comet is going to be is how close it is to you. It was also at its closest to Earth a couple of days ago. So it's going to continue to get a little bit dimmer just based on the fact that it's moving away from Earth. But they're at their brightest when they're the closest to the sun, because the sun is exciting all that fun stuff on the surface of the comet, causing it to outgas, causing it to push dust and other debris out. That's what you're seeing. You're seeing sunlight being caught by that debris. So we're going to keep an eye on this. It could be sometime next week that we're able to see it. The challenge is they're at their brightest when they're closest to the sun. They're also hardest to see when they're closest to the sun, because they tend to be very low on the horizon, and also tends to be very close to either dawn or dusk. This particular one's going to be a morning comet, so you'd have to get up a little bit early before sunrise, which I know I'm not super excited to do right now with temperatures in the teens and 20s, but you don't get to see these things too often, so keep that one in mind. The other thing, and I'll have some post on WRAL.com explaining what's going on here, along with some better times and where to look. So look out for that. The other thing that's happening on Monday is an occultation. So an occultation is kind of like we'll call it a planetary eclipse. The moon is going to move in front of the planet Mars on Monday. It's going to happen around 10 o'clock in the evening. Again, I'll have something on WRAL.com. Those are lots of fun because you can see the planet disappear, and then a little more than an hour later, it reappears on the other side. This is going to happen close to a full moon, so the full disk of the moon will be lit. Sometimes those occultations happen during another phase of the moon, and it will disappear behind an unlit portion of the moon. And that's really kind of freaky, because you'll see this bright planet just wink out. So that's happening on Monday. I will leave you with this while we take in some questions. I understand we have some online as well. Here's a couple of websites that you can check out. I mentioned the Space Weather Prediction Center. Tons of great information there. There's a lot of highly technical stuff. There's a couple of different dashboards. It is intended for different users. It's intended for people who are just interested in seeing Aurora. There is probably somebody down at Duke Power in downtown Raleigh right now that has the SWPC website up and is monitoring it, because that can affect power lines. Colonial Pipeline, that is responsible for all that gasoline that's coming up to us from the Gulf states. They probably have one as well. If there is a coronal mass ejection, is there some sort of solar storm? All that energy's got to go somewhere. Duke wants to make sure that they direct that into the ground or elsewhere into the system so it doesn't fry their equipment. And actually the oil pipelines can be charged by this as well. So they're paying attention to that. So check out the SWPC. And all the images that I showed you from SDO and from SOHO, those are available online as well. There's the two websites for that. I mentioned that things were pretty conservative on the SWPC website. They don't want to overhype things. And that's good, because we've had a lot of disappointments with Aurora predictions. Little less conservative is, and a site that I like a lot is University of Alaska Fairbanks, their Geophysical Institute. They have some hourly forecast maps. It defaults to Alaska, obviously, but they also have some North America maps there that go hour by hour and pay attention to not just that green blob of this is where the overhead aurora might be. They have another line down at the bottom that indicates the limit of where you'd be able to see something on the horizon. It's pretty cool to see the aurora on the horizon as well. So that's another great resource. With that, I've got some time for some questions.
Let's give Tony.
And I believe there's somebody's going to come around with a microphone.
Check. Let's give Tony a round of applause first.
Thank you.
Thank you very much. Exciting stuff. Yes, we have time for questions, so just wave at me if you're in the room and you've got a question for Tony. I'll bring you a microphone. And then if you're watching online, I've got your questions pulled up right here. That way we can get them into the program as well. We'll get started here.
So I had a question about the space weather prediction website. When it shows the picture of the map of the United States, is that specific to an area, or is it just a general where is it going to be visible in the United States? Could you put like a zip code in or something to see what your area? Yep, that's okay.
Okay, so you cannot put in a specific zip code. We don't have the ability to forecast down to that level. So it is very much measuring with a yardstick, not a micrometer, is one way to think of it. And you'll notice that the green blob there is rather blurry. So these are very broad predictions. Oh, sorry.
Okay, that's all right. We're not from here. We're from Pennsylvania, and
You get to see a lot more then.
I haven't seen any. But that's why I'm wondering. We get a lot of cloud cover, obviously, in those times, because I did hear about
That
this.
is the enemy of astronomers,
Yes,
is cloud cover.
but that's why I was wondering, if it's just going to be like that kind of picture, and you just kind of have to figure it out.
So what you're seeing there, that green is likelihood. So super conservative. They're not even expecting it to be very likely over northern Canada. As you see that green blob move down, and as it gets more red, that's when you should really start paying attention. Yeah. But unfortunately, you can't poke in a zip code. We've gotten really good at, I believe the National Weather Service, their forecast areas are down to like a kilometer. It's amazing what can be done now. There's a lot of computer models involved in that, and that's decades and close to a century of work there. We're just getting started with space weather. Good question.
Great stuff. Carson Online wants to know, will the visible auroras this winter be more vivid or more active?
That depends on the... Did we die? There we go, we're back. That depends on the energy that is contained in that coronal mass ejection. And we won't know that until it passes that Discover spacecraft, that NOAA Discover spacecraft that's got all the instruments that measure these sorts of things. And that's sitting out there at L1. That gives us about 30 to 45 minutes warning of what it will actually look like. But in general, when it comes to observing in the winter, we tend to be pointed to a part of space that is away from the galactic center. So it tends to be a little less cluttered in the sky, a little darker, and the air tends to be, observing in general in the winter is a little more pleasant than observing in the summer. Just the skies tend to be a little bit darker, so presumably that can make for a little better observing of aurora as well.
They also want to know your recommendations for places to travel for the best chance of viewing. Should they go to Iceland, Canada, Alaska, Norway?
So my sister lives in Maine now, and she sent me some pretty amazing pictures from there. Canada, you need to be going up into the upper reaches of Canada. They have the same problems that we have. Most of the Canadian population lives near the border. So you've got to go up into the upper reaches of Ontario, Quebec, so on and so forth, to get out of there and farther north to be able to see more of them. Alaska has built a tourism industry around Aurora. So you're going to find some tours and things like that that might help you out there. The bottom line is the farther north you get, the more likely you are to see Aurora. Even if you plan that once in a lifetime cruise or visit to Alaska or Northern Europe or whatever, during quote unquote Aurora season, there's no guarantee that you're going to see Aurora. It's a roll of the dice.
Oh, wow, interesting. All right, next one in the chat for you. Barbara wanted to know which direction in the sky should we look to see the upcoming comet, Atlas?
That sunset, or sunrise in this case. The comet is passing its closest point to the sun, so it's very close to the sun. So that glow on the horizon that you see, that's the rising sun, that's the direction you're going to want to look.
Look at the sun, but don't look at the sun.
Look at the sun before the sun rises, or you won't see nothing. Yeah, there's been some talk of this being possibly a daylight visible comet. I think they're basing that totally on the numbers that are being seen, because yes, you can see Venus during the day, but that's going to be pretty difficult, I think. And let me ask the question, answer the question I thought you were going to ask, and that's what direction in the sky do you need to look to see Aurora? Always north. Always north. Now, it may span across the northern horizon a bit, but know where north is and look towards that direction.
I guess I always associate auroras with winter. Is that true? Like if you said, Chris, draw a picture of an aurora, I'm going to add a snowy landscape to the bottom of the photo. But it sounds like maybe I shouldn't, that these things can happen any time of year.
They can, because remember the last time we saw it was in October, and before that it was in May. So perhaps the reason you're equating that is the best place to see auroras is in the northern part of the world, where it tends to be a snowy landscape. So pictures you have seen, all the beautiful pictures of the dancing ribbons of purples and greens and reds,
right,
have been from those areas where you can see that with the naked eye and then get really beautiful pictures if you follow some of the tips that we threw out there. Those things tend to happen in Northern Europe, Northern Canada, and Alaska, where there's snow on the ground a lot longer than it is around here.
Now, what does NASA and the other space agencies around the world do for their spacecraft to protect them from space weather? If it can be so damaging, if solar panels are eventually going to lose a lot of their productivity, how do they prepare and plan for that?
There's only so much you can do, because I don't know if anybody remembers the series 24, action adventure kind of series, where each episode was a single day or single hour in a day.
Right, right.
They were consistently talking about moving satellites. Let's move a satellite from point A to point B, because we want to look at some different. It ain't that easy. Moving a satellite takes days and spends a ton of fuel. And spending fuel is what kills a mission. You want that mission to last as long as possible. You want to get the most science per dollar out of it. So you can't really move it. Now, they might reorient the spacecraft temporarily to remove, kind of the side of the barn aspect of those solar panels. So less of the solar panel is facing that CME, but generally they don't. There's not a whole lot that can be done there. Now, when we're talking about people who are in space, the folks that are up on the International Space Station, that's the other thing that the Space Weather Prediction Center is doing, is they're in good contact with the Johnson Space Center that is constantly monitoring the International Space Station. If there is a threat of some sort of space weather heading directly for the space station, there are areas within the space station that they can go that are more highly protected. And if it's bad enough, they can leave. Hasn't been that bad. Interestingly, the spot in the space station that provides the most protection from these kind of radiation events is where they store the water. Water makes a really good insulator for radiation and all this other nasty stuff that's heading that way. And water is delivered up to the space station in these big plastic bags. You might use them camping, very similar kind of thing. And they've got areas of the station that are lined with these things, just storage for later use. So they'll go in there and kind of hang out there until the threat's over.
Other questions?
I have two questions. So on your first slide, you mentioned that on the sun, there's sunspots. And you had another image, and I think it was hotspots on the Earth. Is that how we're able to predict where we can best see auroras?
So it might have been this slide here. So these are both of the sun.
Okay.
So they're just different instruments that are telling us different things. We can see more of the structure of what's happening within those ribbons of magnetic fields where this material is traveling along until it can't be contained in the sun anymore and is eventually spit out, belched out, if you will, by the sun in a coronal mass ejection. The image on the right is through a instrument that is looking at the sun more in a magnetic view. So that's showing us where those sunspots are. The other image that you might be thinking of was this one, and that's just another view. That's just showing those sunspots. Now, when it comes to where on the Earth is the best place to see these things, the farther north you are, the more likely you're going to be able to see those auroras, because what you're seeing is happening in the upper atmosphere. Despite what you may hear, the Earth is not flat. So we do have a field of view, we do have a horizon, but because these things are happening so high in the upper atmosphere, we're able to see them much farther south. So a lot of the events that we're able to see down here on the horizon, auroral events, are actually happening in Pennsylvania, in New York City, up in Maine. So when my sister will call me and say, oh, you should see the aurora now, I'll go outside and sometimes I can see it low on the horizon.
So the only way we can predict is if we pay attention to, I forget what the
Space Weather Prediction Center is one way. And I will tell you that, so I work with about 500 TV meteorologists around the country. They are nuts for this stuff. It is what I get the most questions about. And they want to know, okay, how can I get early warning of this? Can you send me a 3-day forecast? Nope. I can send you the SWPC's 3-day forecast that says, this is what we think is going to happen based on what we saw happen a couple of days ago. But we really don't know how to characterize that storm and tell if at all, and then what kind of and how beautiful it might be auroral activity is going to happen literally until 30 to 45 minutes before it actually hits us. Because that's when it passes that L1 point, it passes Discover, it passes SDO, it goes out there in geosynchronous orbit, which is between the Earth and the Moon, very much closer to the Earth. That's literally just a less than 5 minutes warning. When we're able to measure those things that are important for understanding how that aurora is actually going to be displayed, if it's going to be displayed at all. So be aware that it might happen and go out and look.
And also, you mentioned atmospheric drag, and you said how it's like an imbalance. What causes the differences in the densities?
It's thermal, mostly. So the thermal energy that's being imparted into that upper atmosphere by this plasma and by the solar wind will cause the atmosphere to expand and contract.
Okay, thank you.
Good questions.
You mentioned that the polarity is one of the factors that will determine what happens. Does the polarity determine whether it's a borealis or australis? I didn't say that right, but you know. Or how does the polarity affect the visibility?
That's a good question. I should have gone deeper into that. Thank you for bringing that up. The direction that the CME was sent out is pretty much what's going to determine whether it's going to be seen in the north or whether it's going to be seen in the south. More often than not, they're glancing blows, where the CME is going to hit in such a way that it's all going to funnel through that northern part of the donut, or it's all going to funnel through that southern part of the donut. And the time of year matters too, because the Earth's tilt, it may be tilted towards more towards the sun in the northern hemisphere during summer months. Perhaps why we've seen a few more interesting things, like back in May, that might have contributed to it. But the polarity matters because the polarity of those particles that are heading towards us, if they are charged in a way that is compatible with the Earth's current and the upper atmosphere's current charge, it's just like any other magnetic thing. You put a north to a north, and they're going to point away from each other. They're not going to attract. If you point a north or a south, they're going to attract. So if you've got a negatively charged storm coming at you and the Earth currently positively charged, that's going to lock on better, and that's what causes that energy to dip farther into the donut. So we're down here at 33, 34 degrees latitude. You see lots of things up at 80, 90 degrees, but it's hard to see it down deeper. So if it's charged in a way that it's going to lock on and funnel that energy deeper into the donut, that's when we're going to see more aurora. Other questions?
I can ask another one.
Please.
Okay. You've kind of alluded to this, but can you say anything more about what the actual speed of the CMEs is, or is it very variable because it's made
It's
up of a bunch
variable.
of components? Or?
Yeah, it's variable, and it depends on the amount of energy that it was expelled with. I mean, you've seen those ribbons twisting about, how violently that escape occurred, and it's generally about 3 or 4 days before it makes it here. And again, all of the information we have at that point is visual. We've seen what happened there, and we can compare that to previous CMEs that looked that way, and how they actually ended up at Earth to try and make some predictions. But yeah, about 3 or 4 days before it makes it here, and then passes Discover, passes SOHO. We measure in situ. Okay, now we got some real data. 30, 40 minutes later, it actually hits us. Sometimes they're surprises. Often they are not. We're getting better at it.
I have one more.
Please.
If you have any theories, or if you've heard any theories, why the prediction curve was so far off this cycle?
There have been many papers written on this, so there are a number of different theories out there, and I really haven't seen a trend towards what the explanation might be. That's the cool thing about science, is we're trying to figure it out, and I think I've said it a couple of times. I don't think I can say it too much. The sun is something that we don't know enough about, so we're learning more and more about that every day. Actually, the information that we're getting back from the Parker Solar Probe that is flying through the corona, it's flying through the atmosphere. Hopefully it will answer one of the most fundamental questions we have about the sun, and that's, why the heck is the atmosphere so much hotter than the surface of the sun? And maybe that'll help answer the question about, why did we get the prediction so wrong?
Let's give Tony one more round of applause. Thank you very much.
Thanks.
As we wrap up, Tony, there's a request. If you could put the slide up that showed the map of the Lagrange points.
Oh, sure.
Somebody wanted to see that one. This one? The other one. The other one. They're from Pennsylvania. They don't care about North Carolina. Yeah, no. It's no good. Well, everybody.
So a mile from your house is L2. 93 miles to your house is the sun.
There you go.
But you need one of these in Pennsylvania. And you can't have this one. We like this one.
And you can't have this one. It's only here at the North Carolina Museum of Natural Sciences. Thanks, everybody, for participating in today's program. Thanks for coming out to the museum and joining us, or tuning in online. We won't be here next Wednesday at noon with this program. We got to take next week off. The museum itself will be closed to the public next week because we're all going to spruce the place up, so I'm told. I don't know. They said, here's a mop and a broom, get working. Something like that. But we will be back here in 2 weeks, so don't miss out. Head to naturalsciences.org. You can see upcoming programs and events there, including the Lunchtime Discovery Series, as well as the website for the Office of Environmental Education, which is eenorthcarolina.org. And then, hold on, I'm going to get to it. On Thursday, January 23rd, we'll be gathering here at the museum at 7 p.m. in the Daily Planet Cafe for a science cafe all about the Artemis mission with Nick Eakes from Moorhead Planetarium. So if you like this kind of thing, join us there. That'll be exciting to learn more about NASA's mission to the moon. And then, Saturday and Sunday, February 1st and 2nd, from 10 a.m. to 5 p.m., we are celebrating, this better be what you wanted me to say, Astronomy Days here at the museum 2 full days of literally all things space. The museum's astrophysicists, NASA solar system ambassadors are all going to be doing presentations. We're bringing in special guests from outside North Carolina who are going to do talks about their space science, plus games, crafts, activities, and exhibits for all ages across both buildings of the museum. It's going to be big, fun, exciting. We're going to have a great time. Don't miss it. Astronomy Days, February 1st and 2nd. Thanks, everybody, and have a great rest of your Wednesday. Bye.